All right, everybody, we have our usual part 2 roadmap review. Fall 19 test 3 seems to be very popular for some unknown reason. It's not really unknown. Start here. We're doing 2 reactions at a time. Oh my goodness. So you got to remember your ortho, meta, para directing abilities of nitro, because you're putting a nitro on in step 1 here. Nitro is a meta director. Your second group, which will be a ketone, goes meta. So let's draw one nice benzene. How nice do we want it? We'll try to do a really nice benzene up here. Maybe threw me an arrow. Look at you. Yeah, okay. My goodness. You're not going to get a nice benzene. You're going to get a semi-nice benzene. Oh, not my intention. Yeah. Yeah. Everywhere we're going to still have a benzene. Still therapeutic here. And one more just for good measure. Yeah. Okay. So you're putting a nitro group first. And an acyl group, in particular, acetyl group, meta. CH3 carbonyl Cl. Yeah, this is the protocol to reduce the NO2 to an NH2 is one of the parts. And we don't have a reaction that does that and reduces a ketone to a CH2, so don't pretend we do. 2 separate things. H2 and nickel, good idea. H2 and platinum, good idea. Iron and HCl, a good idea. You know what's not a good idea? Lithium, aluminum hydride, and HCl, because it'll reduce this to an alcohol, and you don't know how to get rid of an alcohol and make it into a CH2. So H2 and nickel's a good one. That'll take care of your NO2. And then you got to do Wolff-Kishner. Yeah, I do like the Wolff-Kishner this time. Wolff-Kishner H2N NH2 and OH minus AQ, excess AQ, little heat. The reason I don't like the Clemenson quite as much for this time is because amine is a base and you just made your NO2 into an NH2. If you use HCl, you're going to protonate it to lose some of your acid. Then you'll have to deprotonate it later. So you save the step. And now you've got this, and let's see. This is not about electrophilic aromatic substitution here. This is good old chapter 18, carboxylic acid derivatives. How do you make an amide from an amine? And you just need a reactive electrophile with a leaving group on it that contains this entity here. You need a leaving group on that entity. And how about an acid halide? Now some of you are saying, wait a minute, isn't this how you put groups on benzene with acid halides? Yes, you can put groups on benzene with acid halide in the presence of an aluminum chloride catalyst. Leave the aluminum chloride catalyst out, you don't get anything on benzene. It's a straight chapter 18 acylation of an amine. All right, now we got aluminum chloride. We're going to put a methyl group. Which of these two directors is more powerful is the question. And any nitrogen with a lone pair is more powerful than a hyperconjugating R group. So this is the OP director that takes over right here. So you put a methyl group in the para position for major. We got two boxes. I didn't label major and minor. Maybe on the answer key I said I wanted major and minor. Yeah. But I know why I left them out now. I already gave you clues. Look, look. Where's the methyl group here? Para to the NH2. Yeah. Down there. We got an ethyl group over here. We got an NH COCF3 here. You could write it that way or this way. This one, same story. Uh-oh, it's way up here. NH COCF3. Methyl group has to go ortho. Put it right there. Ethyl's here. And since we're down here, how do you oxidize both the methyl group to a CO2H and the ethyl group to a CO2H? Oh, yes. Red hot. K2Cr2O7, H2SO4, AQ. And it's very important on this one, you also say heat. You need that heat. Nothing happens without that heat. Quite a bit of heat too. All right. Hey. Do you remember this is a carboxylic acid derivative called an amide? Do you remember what makes all carboxylic acid derivatives the same? They undergo hydrolysis and you get a carboxylic acid here and an amine here. Oh, I need the amine here. Hydrolysis. Acid or base I'll take. You can go H2SO4AQ. Hydrolysis. Since we're here, how do you get rid of an amino group? Oh. This is one of the 7 results after diazotization. Yes, sir. You said change it to diazonium and then H3 PO2. Correct. So diazotization. And ladies and gentlemen, these boxes are too small. I'm going to make sure your boxes are a little bigger at least. You're going to have less boxes. I think that's already promised on the review guide. And the page will still be a page, so the boxes will be bigger. Because I don't even know if I'll be able to squeeze this in here. NaNO2 HCl AQ 0 degrees Celsius. And then H3PO2. So you made a diazonium ion. And then hypophosphorus acid, where it gets rid of the NH2 and puts an H in its place. Gets rid of the diazonium and puts an H in its place. The NH2 is gone in step 1. How about this one? It's another diazonium protocol. Same first step. It's worth writing out many times. Just to remind you, you're going to be writing it out many times too. And the protocol here is KCN, CuCN. All right. What's going on from a nitrile to a primary amine? There's two new H's here, two new H's here. You took two, there was two pi bonds. I would go with our old standby H2 and platinum. Reduce that nitrile to an amine. And then, oh, the amine attacks this carbon. One away from a carbon that has an OH. This is an epoxide opening. Step one, hit it with the epoxide that has the right number. Oh, that's not epoxide. One, epoxide. Looks like it has one more methyl right there. And two, always HCl. And then PBr3. Wait. PBr3 reacts with alcohols to make alkyl bromide. We got alcohol. We got alcohol. Oh, yeah. And that's going to be a Br. And then aluminum chloride is a catalyst to put carbon groups on. From halogen carbon groups. Just like we did here. Put this methyl on. Here we're going to put this carbon on because you're going to put a Br there first. Catalyst delivers this carbon. It'll be a really nice ring size right there. Okay. It'd be an awkward ring size down here. I'd accept the answer if you put the ring over to the left as well. So I would take it if you made a bond from here to here or from here to here. I'll even give it if you put it from here to here, because these are all ortho para directors about the same. They're all carbon groups. But I'll just do the one that's most easily seen from the molecule drawn above it. And on top, you've got a CH2 that goes to an NH, goes to a CH2, goes to a C that's attached to the benzene. There you go. Pretty nice. Did I do it right? I think so. CH2NH, CH2NH, CH2C with a methyl, C with a methyl, C attached to the benzene. Ring size 6. 1, 2, 3, 4, 5, 6. It looked like 5 to me. That's why I didn't like it. 6 is a little better, but it is 6. Okay. Wow. How are we doing? Want to do the top part first? Start here. Put a methyl on first and then nitrate. And a methyl is an ortho para director. So if you put the methyl here, major is nitro para. Put the methyl here, minor is nitro ortho. There you go. And there's a big clue on the next reaction that this was ortho. They're ortho here. Big clue in the next reaction that they're para. I hope it doesn't mess you up that the methyl's down here. Fluoro's here. Ah, NO2 becomes fluoro. We don't know how to do that. The only fluoro you ever learned how to put on benzene is from a diazonium ion. And I got to apologize here that you can't do this in 2 steps either. Yeah. You got to reduce that NO2 group first. H2 nickel's good for that. You got to diazotize it next. I told you you're going to do this a lot on this test, both in this section and in the mechanisms. NaNO2, comma, HClAQ, comma, 0 degrees Celsius. It's always the same. And then the one that converts it to a fluorine, what chemical is that? HBF4, fluoboric acid. H plus and the BF4 minus ion. Cool. Are we putting a fourth group on benzene? The third group on benzene. Which group's a more powerful director? A methyl that can stabilize cations, or a fluorine that destabilizes them with its electronegativity, yet partially stabilizes because it can resonate with them? I think I answered my own question. Methyl is the one that's more important because it's more powerful. I want to go para to methyl, but that's already gone. You can't put another group para. Don't be doing that. Get octet violations. A little late in your careers to be getting octet violations, I hope. So you got to go ortho. So you got your methyl. You got your fluoro in your new group. Ortho to the methyl is a Br. Yeah, I know, we forgot about this. We'll get there later. Oh, wow, there's some chemistry we've already done here. Looks like a new bond was made from the phenyl to a carbon, which is one away from a carbon that has an OH. Wait, this is like a broken record. We did that over here. We used a nitrogen nucleophile right here. Where were we? U. NH2 attached to a carbon one away from an alcohol. So I need a nucleophilic carbon. Uh-oh. Yeah, I need this carbon to be a nucleophile. This one. How do you convert an alkyl bromide into a carbon with a minus charge? How about lithium and hexane to make an organolithium? Lithium and hexane. How about opening up the epoxide? Step 3, after you open up an epoxide, you got an O minus HCl. Sorry, I should have three numbers in that box too. That's not 3 points though. HCl is like, it goes with the previous one. They're one thing. And let's do that part I forgot before we move down. I forgot this part. Oh, this is good. This is good test for your retrosynthetic analysis question. Which of these two groups do you have to put on first to make sure the next group goes in the right spot? The acyl group, yeah, because that's the meta director. If you put the isopropyl on first, this acyl group doesn't go meta, it's going to go para. So let's put the acyl group on first. ACYLE. It's called the Friedel-Crafts Acylation for that reason. Well, and two dudes. There we go. So it's a 4-carbon group. And now I need a isopropyl with a leaving group on it. And the catalyst that puts carbon groups on benzene, we already have one right on the same box. The same catalyst for acylation and alkylation. That's what this is, alkylation. And then, CrO3AQH2SO4 in heat does the same thing as potassium dichromate, sulfuric acid, AQ in heat. And the answer is any carbon that has a benzylic H gets converted to a benzoic acid. This carbon, right, where am I? This carbon here does not have an H, stays as is. As is. This carbon has a benzylic H, it gets chewed up and becomes a CO2H. Don't worry about what happened to the other two carbons. They also are carboxylic acids, but don't worry about it. They're side products. There you go. Yeah. Top half of the page done? No. No, this is brutal. Well, what's going on here? This one's not as hard as it looks. Looks like you took a benzylic H off and put a benzylic bromine. Any suggestions? Time to get radical. I would take Br2 in heat. Br2 in heat would work. NBS in heat works a little better. N-bromosuccinimide in a little heat. And you got that. Looks like it's making Grignard right here, attacking the least hindered carbon right here, and getting an O- right here, protonating it here. So all that said, you got an NO2, which didn't change. You made a Grignard from this position here, makes a new bond here to a new group. CH2 goes to C with an O that now has an H, and two ethyl groups. There you go. And that's that. Oh, look what I'm doing again. That's electrophilic aromatic substitution. I just need to make this into a cation. We've made alcohols into cations before. You protonate them, and the thing leaves because it's tertiary. So some strong acid here. HCl might work. Sulfuric acid works generally. But more interestingly, phosphoric acid seems to give the best results on these. You don't really need to know that. We'll just go sulfuric acid. Protonate, makes cation, electrophilic aromatic substitution happens, and you're there. And then we got our NBS. Oh yeah, puts a benzylic bromine on. Can't put a benzylic bromine here. It's already quaternary. You can put it here. So NBS is going to react here. Take that off, put a Br there. Grignard, sorry, organolithium, and epoxide opening number 3 on the same page. 4. There's 2 here. There's 1 on the far left. And this is the 4th one. It's an important reaction. I guess just want to review it until you know it's really important. All right, so you got our ring, our fiber. New bond here to that epoxide. O becomes OH. And it's got a nice propyl on it. Okay, there you go. I bet there's some clues underneath too. Oh my goodness, what's he doing here? Oh. Oh. What's happening there? Yeah, good question. Well, clearly NO2 needs to lose its O's and become NH. We do that a lot on this test. H2 and nickel makes NO2 into NH2. It's not going to do anything with an alcohol, but if that's a halogen, there's a good chance it'll close. If it's a ketone, it's a good chance it'll close, but it'll make an imine. That's not a problem. You like that one? Ketone, make imine and then reduce the imine? I do like it. Ketone, after you do PCC, makes ketone, and that will automatically condense. You can assist it with a DST and H2 and PT to make sure your double bond on your imine is now CH and NH. There you go. So much good stuff. Looks like we're making a diazonium dye. I believe I skipped diazonium dye. won't be on your test. But Mr. Hamoud in lab, we're going to make a diazonium dye. Second last experiment this semester. So there you go. Oh, I hope you don't mind, your last name just slipped onto a video. You're okay? Okay, so yeah, let's get to this, at least to the step before it. And I'll tell you how to do it, but you don't need it. You should be able to do this. This reaction seems to be happening multiple times on the page too. Benzoic carbon becomes benzoic acid. K2, Cr2, O7, H2SO4AQ. Needs heat. And you made this molecule here. You can call it para-amino benzoic acid or ortho-amino benzoic acid. OABA, as opposed to its brother in biochemistry, PABA, para-amino benzoic acid. And hey, we're just doing a diazotization. That's the N triple N plus. Na, how many times has this been on the page? I've lost track. NaNO2, HCl, XS, AQ. Don't forget, you're making the diazonium. You don't want it to break down. Needs 0 degrees Celsius. And then this is the part, this is the, I guess the comment here goes here. And so basically, it's not, it wouldn't have been hard if we had this on the exam. You just copy the aromatic ring, it's a naphthalene here. I didn't even draw a nice naphthalene. That's embarrassing. Naphthalene. I'm really struggling here. There we go. There. And we have an OCH3 on the meta to the bridgehead position. There, that's not your purview, and I don't think this is your purview either. Maybe it is. Yeah, this is a normal EAS reaction. This comment doesn't go here. Please give me my star. Whatever. There. There we go. This is okay. You should be doing this. You can do this. It's sulfonation. All you need is the bottom of the ring. There's a new group here. See? Right there. Ortho to an OCH3. And it's H2SO4. And heat. On this page a couple times. Big long roadmap. And I'm putting a star here. You're not responsible for that. I skipped diazonium dyes, won't be on your test. So this is also about diazonium dyes. And just a long story short, if you're curious, you get your N, and you got R2 and R1, and the one that's farthest away from this lone pair, by way of resonance, picks up a proton. So it's not a double bond there. In fact, this answer I'm about to give is It's not ideal because with resonance, you double bond there, an H there, and it's just a wrong answer because R prime changes too. But I'm not going to belabor a reaction that's not on your test. So I don't want to spend 5 more minutes fixing this. Okay. Where are we at now? We're at the halfway point. Any undiagnosed things here? Here we go. Yeah, we didn't do here. Oh, there's a whole different roadmap over here. Wow. Okay. What's going on? We've got lithium aluminum hydride reduces a lot of things. It reduces carboxylic acids to alcohols. It reduces amides to amines. Got a lot of excess here. Let's do it. A lot of excess. All the way to an alcohol. All the way to an alcohol. NH. COO. CF3. No, there's no COO. CH2. My bad. Lost track of where we're going. Maybe that new color, just so you know, that's new stuff. Yeah, the O is the one that leaves. N is a terrible leaving group. NHCH2, there was a big clue here, wasn't there? That's the same group. Oh my, such good apple. Wow. Oh my, such good apples written there. I wonder why. Why did I stop there? Oh my, such good apple. Oh, dicarboxylic acid with 6 carbons. 2, 3, 4, 5, 6. Yeah. And you're making esters. So you can do the Fischer esterification. You can do that. You could have used an acid halide here, acid dihalide. 1, 2, 3, 4, 5, 6. But this one would mean something like hot, no DST. Fischer esterification times 2, or an acid halide times 2, and nothing else. You can put Cl here, Cl here. Reaction happened like that. This one's taken hours. And there's issues with your amine and your catalyst. So you might have to use excess catalyst too. Yeah. Okay, what do we got? This guy going to this guy. What's going on? Got an extra carbon here. Extra carbon. So if I can make this a leaving group and add a nucleophile that's got a carbon attached to nitrogen, cyanide, and then reduce it to an amine. I think I just gave the whole deal. Got to make this a leaving group so you can do a cyanide SN2. PBr3 is a good one. KCN is good for your SN2. H2PT reduces the triple bonds down to a single bond, and H is 4 of them. New. What about here? I need an NH2 where I had an OH. So some of you want to try PBr3 and then NH3. You want to try that? I might give you half credit. In our notes the other day, we said alkylation of ammonia creates a dog's breakfast. It's in your notes. It's not a good reaction. Azide is our favorite way to make a primary amine. azide. But you need a good leaving group, just like the previous one. KN3. And once again, I was not so great on this. H2PT is a good way to reduce azide to NH2, and you lose nitrogen gas. I think we'll finish this part and do a mini video on the other part. Where are we at? When does it end? It never ends. Okay, we need to make, whoa. This one, I'm gonna put the big fat star in it. It's related to the diazonium di stuff again. But I think you could probably figure it out if it showed up on a test. I need this to become an N-triple-N so that it can get attacked by the benzene. This would be about the 5th time we put this on this page. NaNO2 HCl-XSAQ 0 degrees Celsius. And I bet if you just warm it up to room temperature, I know there's OH present, but I think the diazonium getting attacked by the benzene would happen first. So the benzene is going to attack. There you go. Once again, you don't need it. Oh, I'm setting up for a Hoffman. You know how? How I know? Hoffman Elimination, that is, not Hoffman rearrangement. I've got an amine, and I need to put as many methyl groups on it as I can. You look at some older videos, it's called exhaustive methylation. And then you do the silver oxide, which does 2 things. Ion exchange, changes hydroxide for bromide. Now you got a base. And elimination, grabbing the least hindered beta hydrogen. Anyway, we got to set it up first. We need as many methyl groups as we can get on there. One of the favorites is CH3I excess. This is alkylation of ammonia, sort of, an amine. And you can make sure it goes to a quaternary ammonium by using an excess of the electrophile, CH3I. Quaternary ammonium, my goodness. Yum. Cations. All right, major alkene, minor. So you got to realize these are the relevant H's. These are the only 2 relevant H's. They're beta. Alpha's with the leaving group. Beta's 1 away. Which one of those beta H's is easier to get to because there's less stuff around? It's the bottom one. So that's where your major alkene's coming from. Double bond. Could have circled that benzene and not have to draw it, but it's not bad. And the amine is going to be, no, regardless, it's NCH3 3 times. And this one is the minor, even though it's a lot more stable. It's a much more stable alkene, but it's still minor because this is under kinetic control. Approachability versus thermodynamic stability. All right. Now, let's see if all these boxes are done outside the mini box. Any gaping holes here? That was only like a 45-minute video, huh? Yeah, there we got it. Wow. Okay, we'll come back and do this other part in a small video.